Hello dear students, this is your engineering mathematics 3 lecture. Today's topic is Z transform. This topic is from second unit. Now what is Z transform? Z transform plays key role in discrete analysis. The development of communication engineering is based on discrete analysis. Z transforms are required to study discrete analysis, whereas Laplace transforms are required for continuous systems. The transforms are useful in the study of control systems, communication systems, signal and linear time invariant systems, and also for solving difference equations. These are the uses, these are the functions of the transform. Now, to define the transform, we require the concept sequence. What is sequence? An arrangement of numbers with certain definite rule is called as a sequence. The sequence A plus D, A plus 2D, A plus 3D, and so on up to A plus n minus 1D, and so on. It's arithmetic progression, or it is a sequence. Or another example, sequence A into A comma, next remember AR, next AR square, AR cube, and so on. At one time it will be AR raised to n, AR raised to r, n plus 1, and so on. It is a geometric progression sequence. Then the third example is here, the sequence U1, U2, U3, U4 up to UN is called finite sequence. The sequence having infinite terms U1, U2, U3, U4, at once it will be UN, then UN plus 1, UN plus 2 up to infinity is called infinite sequence. For example, 1, 5, 9, 13, 17 up to infinity, arithmetic sequence with first term A is equal to 1 and the common difference is here D is equal to 4. Second example, 2, 4, 8, 16, 32, 64 and so on. Geometric sequence with first term A is equal to 2, common ratio is R is equal to 2. Here. It's 2 square, 2 cube, 2 raised to 4, 2 raised to 5 and so on. The sequence are written in, it is written in two ways. The sequence written as U0, U1, U2, U3 up to N is called as listing method. The sequence, this sequence is also written in terms of its kth term as curly brace U suffix K, where K is equal to 0, 1, 2, 3 up to infinity. So we can write this sequence in two ways. The first way is U0, U1, U2, U3 up to UN is called the listing method, and the sequence written in terms of its kth term as in curly brace U suffix K, and K varies from 0 to infinity. It's called as kth term method. This method is called kth term. The kth term of sequence is written as U suffix K or U of K or F of K or F suffix K. These are the notations to represent the sequence. Now what is series? If U0, U1, U2, U3, UN plus 1 up to infinity is a sequence, then U0 plus U1 plus U2 plus U3 up to UN plus UN plus 1 up to U infinity is called as a series and written as like this: U0 plus U1 plus U2 plus U3 plus UN plus 1, UN plus 2 addition of all the terms up to U infinity. In short, we can write this addition as summation of U suffix K, UK, K varies from 0 to infinity. So this is called addition of all the terms in the sequence is called series. This is the concept of series. Now the definition of Z transform. When there is a function f of t, when we define a function, then we find the Laplace transform of function. And when we define a sequence, then in that case, we find the Z transform. The transform is always of sequence and not function. See, what is the definition of the transform? Let f of k be a sequence and let z is equal to x plus I1, where x, y belongs to R means a set of real numbers. I is the imaginary number under root minus 1. Then summation f of k into z raised to minus k varies from minus infinity to infinity, is called as the transform of sequence f of k and denoted by the transform of, this is the notation, z of f of k, z of in curly brace f of k. This is the notation of the transform, and see how it is defined here. The transform of f of k is equal to summation f of k into z raised to minus k varies from minus infinity to infinity. This is the definition of the transform. This term is equal to f of z, capital F of z, always. See the example here. If f of k is equal to 1 by 16, 1 by 8, 1 by 4, 1, let's say we define here 1 by 16, 1 by 8, 1 by 4, 1 by 2, 1, 2, 4, 8, and so on. Here f of 0, where shown arrow, means you count the first member 1 here. This f of 0 is 1, f of 1 is 2, f of 2 is 4, f of 3 is 8. So 1 is f of 0. So 1 by 2 is f of minus 1, 1 by 4 is f of minus 2, 1 by 8 is f of minus 3, 1 by 6 is f of minus 4, and so on. So this is like, then in that case, the transform of f of k, the transform of this sequence f of k is nothing but, you see what is the definition, addition of all the terms. Summation means addition of all the terms f of k into z raised to minus k. Here k varies from minus 4 to 3. F of minus 4 into z raised to 4, because we are putting k is equal to minus 4. K is minus 4, so this term will be f of minus 4, z raised to minus k will be z raised to 4. Because k is minus 4, so minus minus plus, so z raised to 4. So that first term f of minus 4 into z raised to 4 plus, next we put k is equal to minus 3 in this term. So you will get f of minus 3, z raised to minus 3, sorry, f of minus 3 into z raised to 3 plus f of minus 2 into z raised to 3 plus f of minus 1 into z plus f of 0 into z raised to 0 plus f of 1 into z raised to minus 1 plus f of 2 into z raised to minus 2 plus f of 3 into z raised to minus 3, and so on. So it is equal to, see what is f of minus 4. F of minus 4 is 1 by 16 into z raised to 4. F of minus 3, f of minus 3 is 1 by 8. We put all the values here, f of minus 4, f of minus 3, f of minus 2, and so on up to f of 3. So that we will get this term, and then we do the addition of, try to simplify it, then we will get this term. This is the transform of the given sequence f of 2. Similarly, second example is here. Same way, example 3. Same way, as we have solved the first example. Now, Z transform of some standard sequences, like the derivative integration formulae. There are some standard sequences, and these are the results for some standard sequences, and Z transform of these some standard sequences. The results are here. Z transform of a raised to k. Sequence is here a raised to k. Condition is k greater than or equal to 0. Then it is equal to the transform of a raised to k is equal to z upon z minus a. When k is greater than or equal to 0, the condition is mod z is greater than mod a. Z transform of a raised to k when k less than k less than 0 is z upon a minus z. Condition for z, mod z is less than mod a. Z transform of delta function, delta k, sorry, delta sequence is it is equal to 1 for all z. The transform of 1 raised to k means 1 raised to k means 1. The transform of 1 is z upon z minus 1. Mod z is greater than 1. And the condition of k is k greater than or equal to 0. The transform of minus a raised to k is equal to z upon z plus a. Mod z greater than mod a, k greater than or equal to 0. The z transform of u of k is a special function in a step special sequence u of k, it is equal to z upon z minus 1, mod of z greater than 1. This is the condition. Then the next z transform of sine of ak, sine sequence, is equal to z into sine alpha upon z square minus 2z cos alpha plus 1. Here, one correction is there. That correction is here. You take here alpha in place of a, small a. In place of a, sin alpha k, sequence is sin alpha k is equal to z into sin alpha upon z square minus 2z cos alpha plus 1. Condition for z, mod z greater than 1, k greater than or equal to 0. Z transform of cos ak, same correction is here. In place of a, you consider here alpha, cos alpha k, sequence is cos alpha k, and so the z transform is z into z minus cos alpha upon z square minus 2z cos alpha plus 1, mod z greater than 1, k greater than or equal to 0. Conditions. Z transform of a raised to mod k for all k, it is equal to z upon z minus a plus az upon 1 minus az, and condition for z is mod a less than mod z less than 1 upon mod a. Then the next is formula is z transform of c raised to k. C is any constant, c raised to k into sin alpha k, cz sin alpha upon z square minus 2 cz cos alpha plus c square. Condition mod z greater than mod c, k greater than or equal to 0. Z transform of c raised to k into cos alpha k is equal to z into z minus c cos alpha upon z square minus 2 cz cos alpha plus c square. Mod z is greater than mod c, k greater than or equal to 0. Z transform of hyperbolic cost sequence cos h alpha k z into z minus cos h alpha upon z square minus 2z cos h alpha plus 1, k greater than or equal to 0. Then z transform of c raised to k. Then z transform of c raised to k into cos hyperbolic cos sequence cos h alpha is z into z minus c cos h alpha hyperbolic cos sequence upon z square minus 2 cz hyperbolic cos alpha plus c square, k greater than or equal to 0. Z transform of hyperbolic sin alpha k is equal to z into hyperbolic sin alpha upon z square minus 2z hyperbolic cos alpha plus 1, k greater than or equal to 0. Then z transform of c raised to k into hyperbolic sin alpha k is equal to cz sin hyperbolic sin alpha upon z square minus 2 cz hyperbolic cos alpha plus c square, k greater than or equal to 0. Then the transform of a raised to k upon k factorial, k greater than or equal to 0 is e raised to a upon z for all z. Properties of z transform is now these are the results for some standard sequences. Now the properties of z transform. Z transform of f of k is equal to summation f of k into z raised to minus k, k varies from minus infinity to infinity. If we solve this term, summation term, then we have the function of z, f of z, capital F of z. So this is the definition of this is the definition of Z transform. Now, what is the definition of inverse Z transform? In Z transform, here you just shift this Z, transfer this Z in RHS, so that you will get inverse Z raised to minus 1 into f of Z, means inverse Z transform of f of Z, it is equal to f of k, the sequence. This is the definition of inverse Z transform. Now the linearity property, Z transform of A into f of k plus b into g of k is equal to, A and b are the scalars here, constants here. So linearity property is that we can write this A as it is. Z transform of f of k is nothing but f of z, plus b as it is. Z transform of g of k is g of z, by the definition of Z transform. Next property is change of scale property. Z transform of A raised to k into f of k, it is equal to f of z upon A. F of z upon A means you first find the Z transform of f of k sequence, that will be f of z, and then you find the Z transform of A raised to k into f of k, that will be f of z upon A. Then the next property is shifting property, gradual sequence. Z transform of f of k plus 1 is equal to z raised to n into f of z minus summation f of r z raised to n minus r. R varies from 0 to n minus 1. And Z transform of f of k minus 1 is equal to z raised to minus n into f of z. Is shifting property for gradual sequence. Then multiplication by k property, Z transform of k into f of k. If we multiply the sequence f of k by k, then its Z transform is equal to minus z into derivative of f of z with respect to z. We can generalize this formula. Z transform of k raised to n into f of k is equal to minus z to derivative d by dz to the power n of f of z, means minus 1 raised to n into z raised to n into nth derivative of f of z. This is multiplication by k property of Z transform. This is second formula, is generalized formula. Now the next property is division by k. Z transform of f of k upon k is equal to integration of z to infinity z raised to minus 1 into f of z, means f of z upon z. Means you first find the Z transform of f of k, that will be your f of z, and then use the property division by k. The division by property is that you just integrate that f of z upon z or z to infinity. This is division by k property. Next is initial value theorem. F of 0 is equal to limit of f of z as z tends to infinity. If f of k is one-sided sequence, that is k greater than or equal to 0. Final value theorem. If f of k, limit of f of k as k tends to infinity is equal to limit of z minus 1 into f of z, z tends to 1. If f of k is one-sided sequence, that is k greater than or equal to 0. And the next property is Z transform of e raised to minus ak into f of k is equal to f of e raised to a into z. Z transform of e raised to minus ak into f of k. The transform of e raised to minus ak into f of k is equal to. Here you find the Z transform of f of k, that is nothing but f of z. And then in that f of z, you replace that z by e raised to a into z. If the sequence is product, there is a product of two sequences, e raised to minus a k into f of k. So this is the last property of Z trans. Okay. So these are the properties and results of some standard sequences. Now the next example, find the Z transform of that first one, 1 by 3 to the power k sequence, 1 by 3 to the power k, and the condition for k is k greater than or equal to 0. See how to find the Z transform for this sequence. F of k is equal to 1 by 3 raised to k greater than or equal to 0. So use here the definition of Z transform. It is nothing but Z transform of 1 by 3 to the power k is equal to summation 1 by 3 to the power k into z raised to minus k. we are using the definition of Z transform only. And the limits for summation k is equal to 0 to infinity, because condition is given here k greater than or equal to 0. So you take the limit 0 to infinity. Okay. Now k is the power of that sequence, and the power of z is minus 2. So if we take k common, the bracket term is 1 by 3 into z raised to minus 1. Bracket comes to the power k. Okay. Now it is a summation, so we can write the summation. We put k is equal to 0. If k is equal to 0, then the bracket term raised to 0. Means if anything raised to 0, for any term power is 0, then its value is 1. So when k is equal to 0, the value of this bracket term is 1. Plus, when k is equal to 1, it is 1 by 3 into z raised to minus 1. 1 by 3 into z raised to minus 1. Plus, next, when k is equal to 2, it is 1 by 3 into z raised to minus 1 to the power 3, and so on. So you can write in finite terms. Now, it is a geometric series, it is a geometric progression, GP. So, what is the formula for GP, geometric progression? It is first term, in numerator you write down the first term upon 1 minus common ratio. First term is here 1, so write in numerator 1 upon 1 minus common ratio. Common ratio, here common ratio is 1 by 3 into z raised to minus 1. 1 by 3 into z raised to minus 1. In first term also it is 1 by 3 into z raised to minus 1, but its power is 0, because when k is equal to 0, this term is 1 by 3 into z raised to minus 2 to the power 0. And the value of that term is 1, so we have written here 1. But it is actually in the form of 1 by 3 into z raised to minus 1. So the common ratio is here 1 by 3 into z raised to minus 1. Okay. And the condition for k is here k greater than or equal to 0. If this is the condition, then in that case, the condition for z is mod z is greater than 1. Means, sorry, k is greater than or equal to 0 is the condition. See, what is here GP, geometric progression, first term upon 1 minus common ratio. And the condition of GP is that common ratio must be less than 1. Common ratio must be less than 1, because if it is not less than 1, then this denominator term will be negative if this common ratio is greater than 1. So that is the condition of GP, geometric progression, that common ratio must be less than 1. That's why we have written that common ratio 1 by 3 into z raised to minus 1 is less than 1. Now you simplify this one. Z raised to minus 1 means you write z in denominator. So the term is 1 upon 1 minus 1 by 3z. And here z raised to the condition 1 by 3 z raised to minus 1. So 1 by 3 into z raised to minus 1 means 1 by 3z. And so you shift that z, transfer this z in denominator in RHS, so that you will get the condition 1 by 3 less than mod z. And here also the term is 1 upon 1 minus 1 by 3z. And now in this example, if we take 1 by z common, 1 by z is common, and so the bracket term will be z minus 1 by 3, and the term complete term will be 1 upon 1 by z in bracket z minus 1 by 3. And so that z is in denominator term of denominator, so we can write it in numerator. So after simplification of this term, we can write the term z upon z minus 1 by 3. And the condition for z is here mod z is greater than 1 by 3. So we have proved the first formula, that z transform of 1 by 3 raised to k, where k is greater than or equal to 0. Then if z transform is z upon z minus 1 by 3, mod z greater than 1 by 3. This is the first result from this result. The transform of a raised to k greater than or equal to 0 is z upon z minus a, mod z greater than mod a. In place of a, there the value is 1 by 3. The transform of 1 by 3 raised to k greater than or equal to 0. And our answer is there, z upon z minus 1 by 3. In place of a, there is 1 by 3. Mod z greater than 1 by 3. This is our answer. So we have proved it. how it is z upon z minus a. Here, the transform of 1 by 3 raised to k greater than or equal to 0. The condition for k is given. It is z upon z minus 1 by 3, mod z greater than 1 by 3. Now, similarly, the next sequence is f of k is equal to 1 by 5 raised to k, but condition for k is strictly less than 0. See, how to find the transform of this sequence. Now, k varies from k is strictly less than 0. Now, use the definition of the transform. The transform of 1 by 5 raised to k is equal to summation 1 by 5 raised to k into z raised to minus k. K varies from minus infinity to minus 1. Okay. Now, how to solve? Because k is strictly less than 0. K is strictly less than 0 means it is from minus infinity, minus 1 to up to minus infinity. So, the smallest number is here minus infinity. So, you start from minus infinity to up to minus 1. But we know we don't know the value of infinity. So, here we are going to change the limits. Now, to change the limits, you use your substitution. Put k is equal to minus r. If k is equal to minus r, see here in this table, when k is equal to minus infinity, put k is equal to minus infinity. Then k minus infinity is equal to minus r, means r is equal to infinity. When k is equal to minus infinity, r is equal to infinity. Now, when k is equal to minus 1, put here k is equal to minus 1. Minus 1 is equal to minus r, means r is equal to 1. So, if we use this substitution k is equal to minus r, then the limits for r are infinity and 1. But infinity is positive number and 1 is positive number. So, infinity is greater than 1. So, we can say the limits for r 1 to infinity, not from infinity to 1. Here for the limits of k, we have to take minus infinity to minus 1 because minus 1 is the greatest number and minus infinity is the smallest number. We take the limits from lower limit to higher limit. So for k, minus infinity to minus 1, but we don't know the value of infinity here. So using substitution, I change here the limit. The limits are from infinity, sorry, 1 to infinity. Now put here in this summation the substitution. In case of k, you put minus k is equal to minus r. So your variable is there r. So r limits of r 1 to infinity. In summation 1 by 5 raised to k. In place of k, you write minus r. Z raised to minus k. K is minus r. So minus plus. So z raised to r. Now 1 by 5 raised to minus r into z raised to r. Now 1 by 5 raised to minus r. So to make the power positive, you write this 5 in numerator so that the power will be positive. 5 raised to r into z raised to r. And so it is summation 5z raised to r varies from 1 to infinity. And using this substitution, I reduce it as 5z raised to r. Now you write the terms. Put r is equal to 1. If r is equal to 1, the term will be 5z raised to 1 plus r is equal to 2. The term will be 5z raised to 2. Then 5z raised to 3, 5z raised to 4, and so on. And addition of all the terms because it is in summation. So if we do the addition of all the terms, then it is a GP, geometric progression. And then after getting the geometric progression using the same formula like this in previous example, first term upon 1 minus common ratio, you can find the Z transform of this sequence 1 by 5 raised to k. Okay, and you will get it equal to Z upon 1 by 5 minus Z because your k is strictly less than 0. You can prove it. Now, like the previous example, you have to just write the GP series and you have to write the formula for GP series. So these are the results of Z transform. Some properties are there. So discuss all the results and properties here and do some results here. So the session is over here. Thank you.